Welcome to 1007 ICT, 1807 ICT, and 7611 ICT. This is Lecture 12, the revision lecture. We'll be covering lectures 1 to 3, or at least the content from lectures 1 to 3 in this section, and the rest of the course will be covered in the next section. So before we start, I'd really appreciate if you would complete the online course in teaching evaluation. You would have received an email about this at some point in the last couple of weeks. And basically this is for us to get feedback from you about how the course is going and how the teaching is going, and that will help us to improve things for the future offering. So I'd really appreciate if you would take some time to complete that. For this section, this revision session will review the content from lectures 1 to 3. We'll focus mainly on process-based questions. There are obviously theory and content sections on the lectures, but we're not really focusing on that in this revision section, but you should review those sections as well. Coverage of specific topics in this session, or the lack of coverage of a specific topic, means or doesn't mean that it's on the exam or not on the exam. Basically the whole course is accessible, and so we're just giving you a sort of an idea about the kinds of things that will be likely to be on the exam. So all content is accessible and should be revised. Calculators are not allowed in the exam, so that will give you an indication about the kinds of questions that we can ask you. So for some calculations that would normally require a calculator, we wouldn't be asking you those kinds of questions, although we can certainly ask you questions in a similar vein without the actual calculation. So going on to Lecture 1. So Lecture 1 Part A was a course overview. It's not assessable. It basically just covered what was in the course and when and what the assessments were. Part B, though, Introduction to Computers, is accessible, and that one covered what is a computer system, mechanical, electromechanical, and electronic computers, integrated circuits, the evolution of computer processors and storage, quantum, optical, and nano computing, different types of computers, and then computer systems abstractions. There's not really any process-based stuff in that chapter, and so there are certainly content-style questions, and those kind of questions make good multiple choice and short answer questions. The process-based questions tend to make better short and long answer questions. And just in terms of how the exam is structured, there are 50 multiple choice questions worth 50 marks out of 100, and then the rest of the marks, the other 50 marks, are the short and long answer questions, and there are about 20-25 questions in that section. Lecture 2, we looked at data representation, and so how do we represent data inside the machine? Well, actually, as long as we can convert that data to a sequence of zeros and ones, then we can represent the information. If we want to represent some binary integers, like the number 177, we can do that using a series of ones and zeros, and each one in a particular column is worth a certain amount. So if I add these up, this one over here is worth 128. There's nothing in the next column. This one is worth 32. This one is worth 16. 0, 0, 0, and 1. So if I add those up, 128 plus 32 plus 16 plus 1, 10, 6, 17, 5, 6, 7, 177 is the base 10 or decimal value of that binary number. We looked at powers in different bases, and so we looked at base 10, which is the one we're normally familiar with. We looked at base 2. We do a lot of addition, subtraction kind of operations with those. We also looked at some of the shorthand bases, base 8 and 16, and what they allow us to do is to compress the number of digits that we're working with. So for example, every 4 bits in binary can be represented with a single hexadecimal digit. Same thing with the base 8 or octal. Every 3 binary digits can be represented with one single octal digit. In terms of integer word sizes, so we looked at if we have a single bit, we can represent 2 values and they're numbered 0 to 1. If we have 2 bits, we can represent 4 values, they're numbered 0 to 3. And you'll see a pattern here. 3 bits, 8, 0 to 7. 4 bits, 16, 0 to 15. 5 bits would be 32 and 0 to 31. 6 bits, 64, 0 to 63, and so on. And in the general case here is that if we have n bits, we can represent 2 to the n values, and the range will be 0 to 2 to the n and minus 1. If we want to convert from decimal to binary, well, given a number like 165, what we do is there's an algorithm here, but basically it's a simple process of finding, well, what's the biggest power of 2 that still fits inside 165. So we go through it. 1 still fits, 2, 4, 8, 16, 32, 64 still fits. 128 is still fits, it's still less than 165. When we get to 256, 256 is bigger than 165. It does not fit. It will not feature in the answer. So there will be 128, and if I subtract 128 from 165, I will get 37. There are no 64s in 37, but there is a 32. So I subtract 32 and I get 5. There are no 16s in 5, no 8s in 5. There is a 4. Subtract 4, I get a 1. There is no 2 in 1, but there is a 1 in 1. So I subtract 1 and I should end up with a 0. If I don't end up with a 0 in this calculation, I've done something wrong and I should revisit my calculation. So basically that number 165 is 101001001 in binary. There's an alternate decimal to binary conversion in case this one is more appropriate for the way you think. So 79, what we do is we divide it by 2. So 79 divided by 2 is 39, remainder of 1. 39 divided by 2 is 19, remainder 1. 19 divided by 2 is 9, remainder 1. 9 divided by 2 is 4, remainder 1. 4 divided by 2 is 2, remainder 1. 2 divided by 2 is 1, remainder 1. Sorry, remainder 0. Remainder 0. And 1 divided by 2 is 0, remainder 1. So our answer, if you're looking at how this is organized, is 1, 1, 1, 1, 0, 0, 1. Looking at hexadecimal and octal, so basically we see here we have 4 bits per hexadecimal digit and 3 bits per octal digit. In the exam, if you're going to write, when you first are able to write, you should probably write at this table, at least counting from 0 to 15, because it will feature in quite a number of questions, and it'll be easier to look things up rather than work them out from scratch. Looking at binary addition, here have 2 numbers. Work out what these 2 numbers is. We're going to do it in decimal first. So the 2 numbers will be 205 if we work out these bits. 205 plus 137. If I do that in decimal, 205 plus 137 is 342. And so if I were looking at 342, are there any 256s? Yes. So 342 minus 256. What have we got left? We have 86. And so there's no 86s, no 128s and 86. However, there is a 64, so I subtract 64, and that leaves 22. There is no 32 and 22. There is a 16 and 22. That leaves 6. There is no 8 and 6. There is a 4. That leaves 2. There is a 2 and 2. That leaves 0. So there's a 2, and there's no 1s left over. And so the binary value for 342 and base 10 is this number up here. So that's doing it in decimal. If we actually want to do the addition, we could do the addition. So the addition follows the basic rules on the right here. 1 plus 1 is 0, carry the 1, 1, 1, 0, carry the 1, 1, 0, 1, 0, carry the 1. Now if we don't have enough space, so if we only have 8 bits to work in, this 1 here on the front would get lost. If we do have enough space, we just put it in. So on a piece of paper, generally you have enough space. You're not limited by the configuration of the computer. So this is our number 101010110. Just looking at the previous slide to see if that's the same. 101010110. So our computation works. And what I'm trying to illustrate here is you can do this in decimal first, work out what the answer should be, and then you can actually do the computation. And that way, if you get the wrong answer in the exam, for example, you could still get part marks for showing the working out. We then moved on to representing negative numbers, and the first thing we did was we added we used the first bit on the left as the plus and minus sign. So we've reduced the number of bits in total, but we have 1 bit for the plus and minus. So basically that means is if there's a 0 at the front, it's a positive number, a 1, it's a negative number. So this number is 64 plus 8, 72 plus 1 is 73. That's plus 73 because there's a 0 at the front. This number here is 64 plus 8 plus 1, which is again 73. This one has a 1 at the front, so it's minus 73. Now just point out that this actually doesn't work properly in terms of being able to do subtraction, because all we've really done is we've taken a positive value and we've glued a plus sign or a minus sign on the front of it. So we need to do a little bit more work than that. And actually what we'd like to do is invert the value. So when we invert the value, we can use something called ones complement, and what that really does is flip the bits. So if you have a number like this is a positive number, not really sure what that number is, and it doesn't really matter for this example. You'll notice if I flip the bits, 1, 0, 0, 1, 1, 0, 0, 0, you'll see that now it's a negative number, and it should be negative whatever the original value was. Well, if that's the case, then if I add these together, I should end up with 0, because 5 plus minus 5 should be 0, for example. So let's take that 1, 1, 1, 1, 1, 1, 1, 1. Okay, so that's not 0, but actually it's really close to 0. So for example, if I did this and I added this value to all those 1s there, what will happen is 1 plus 1 is 0, carry the 1, 0 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 carry the 1, and that one gets destroyed off the front. So now my answer is 0. So what the process is going to be is ones complement. Yes, it does invert the number, but it doesn't quite go far enough. We need to invert the number or flip the bits, and also add 1. And the part of the reason for that is, remember, from the lectures, we have a minus 0 and a plus 0 with this plus minus sign that we've introduced. And so this is what we've described now is actually called 2's complement. And 2's complement works by flipping the bits and adding 1. So if I have a number like this number is 32 plus 8, which number is 40. It's plus 40. So let's do that process. Flip those bits and add 1. We'll see 1 plus 1 is 0, carry the 1, 0 carry the 1, 0 carry the 1, 1, 1, 0, 1, 1. And so this is my my negative value. So this is actually minus 40, or the opposite value of what 40 was. There's a simpler approach to doing this 2's complement process, and the basic idea is find the rightmost one, this one, keep it and everything to the right, so just keep it as is, and then flip everything to the left of it. Okay, so whatever number this was, this is the negative version of it. This was 40, I believe. 32 plus 8, yep, 40, so this will be negative 40. If we do this again, you'll see that if we keep these 1, 0, 0, 0, and we flip these 0, 0, 1, 0, we will have done the same process but in reverse, and now we have the original number again. So we've gone from plus 40 to minus 40 to plus 40 again. So you can see that you can switch between these. Depending on what the start value is, you'll get the opposite. We also looked at representing character data. So we looked at, here's an ASCII table. The one interesting thing about this ASCII table is that normally tables work with the rows first and then the columns. This particular ASCII table works with the columns first and then the rows. So if we look at, for example, looking for a value, this is 0100, so this is 4, 0111 is 7. So first we'll go this way, so we look at 4, and then we'll look for 7, and if we triangulate we get this one, which is G. And so basically we use the columns first and then the row number. We covered images in terms of looking at bitmaps, for example, and you'll see that each pixel in the diagram at the top has a corresponding bit attached or associated with it, and that bit has a 0 or 1 in it. So in this case, 0 will be black and 1 will be white. So that's pretty limiting in terms of the number of colors or the number of shades of grey. If you look on the right, you'll see that actually this one here has shades of grey, and actually has 16 shades of grey, including white and black. To do that, you have a hexadecimal digit for each pixel. Now, every hexadecimal digit has 4 bits, which means we've just multiplied this size requirement by 4, because every pixel now needs 4 bits instead of 1 bit. But that does allow us to have shades of grey. If we use more information, we can have colors. And so if we have an RGB configuration where we have 8 bits for the red, 8 bits for the green, 8 bits for the blue, then it'll take 24 bits per pixel. We also looked at representing sound or audio, and so looking at this continuous waveform over here, that's not really feasible to put that into a computer. It has a fixed number of bits, so what we do is we take sample points fairly regularly, and the more sample points we take, the better the approximation of that sound wave is going to be. The less we take, the worse it's going to be. So if we were to take one sample point every second, it wouldn't be a very good representation. And the more sample points you take, the more space it's going to take up. And also there's a limit in terms of the human ear is only so good. So keeping track of more information than the human ear can process is probably not that effective. Moved on to lecture 3, which was to do with combinatorial digital logic and also the sequential logic. We talked about different logic gates, and or not, NAND, NOR, and XOR. We also looked at, well, the signals that you have, they'll be represented in volts. 0 to 2 volts could be a binary 0, 3 to 5 volts could be a binary 1, and anything between 2 and 3 volts is an intermediate state, so it's an invalid state, which means you're transitioning from one state to another, so from a 0 to a 1, for example. There were the 3 basic logic gates that we talked about, and, or, and not. And we can build more complex functions from those basic gates. So here's and, or, and not. Basic way to remember and, or the simplest way, is wherever there's a 0 on the input, the output is a 0. For or, it's the opposite. Wherever there's a 1 on the input, the output is a 1. Not, 0 becomes 1, 1 becomes 0, so it's just the inverse. NAND, NOR, and XOR. So NAND, if you look at it, it's basically and not. So the N ideally would be at the end, but that would be called ANDN. So probably NAND is a more a nicer way to say it. But it does mean you have to remember that the not comes after the AND. Same thing with the NOR, or not, and XOR we'll talk about separately. So NAND, the way I remember NAND is probably the easiest way, is just to work out what AND is and then negate it. So flip the bits. Same thing with NOR. I tend not to memorize NOR. I'll work out what OR is, and then I just flip those bits. XOR. XOR is the odd one out. It's the only one that looks like this, 0, 1, 1, 0. So there's 2 1s in the middle. Typically the other patterns are 1, 1, or 3 1s. And so that's one easy way to remember it. Another way to remember it is that, look, if the inputs are the same for XOR, you get a 0. If the inputs are different, then you get a 1. Working with gates, so here's a gate and a truth table. So this part will always be the same. These are the 2 inputs, and I guess it's just counting from 0 to whatever number. In this case, it's going to be 3. 0, 1, 2, 3. In terms of, for an exam, if you have a truth table to fill out, well, this bit's always the same. So if it's not given to you, then you should fill it in. And it might be worth part marks. In terms of the output for AND, we'll remember for AND, wherever there's a 0 on the input, there's a 0 on the output. And so that's the truth table. Here's a circuit. So you might be given a circuit and trying to work out what the truth table for it is. In this particular example, it doesn't matter what the circuit does. We're just looking at the truth table. The first thing is fill in the bits that are always the same. And again, if it's not given to you, then this might be worth part marks. So this one is XOR. So XOR looks like this, and this one is NOR, and NOR looks like the opposite of OR. Right. So this one was OR, and that is NOR. Again, I have no idea what that circuit does, and for this particular question, it's not relevant. There might be other questions to say, well, what does this circuit actually achieve, or what does it do? But in this particular case, it doesn't do that. We also talked about the De Morgan's theorem, and basically the idea here is I've got an OR gate, and I want to turn it into an AND gate. There might be various reasons for that, and so, for example, I might have designed my circuit in a particular way, and it turns out that actually there's a cheaper way to build that circuit using another kind of gate, so I might want to do this conversion. For example, NAND might be the cheapest gate to work with. We then moved on to the logic unit, and so the logic unit in this particular example has two inputs, A and B. There are a number of gates or operations that it performs. There are four outputs, separate outputs from these gates. They go into this box over here. There are some selection lines which allow us to choose which of these four inputs we're going to use, and we'll put one of them out as the output. So that's the basic idea behind the logic unit. Now that box, the colored box there, is made up of two parts, a selector and a decoder. And the selector basically works like this. There's a bunch of AND gates. These A, B, C, D values are the gates or the outputs of the gates from the previous slide, and these S values are four values, one of which will be a 1, the other three will be zeros, like this case. And what that will do is the zeros will turn off the AND gates, the 1 will turn on one of the AND gates. And so something needs to make sure that only one of these four values has a 1, the other three values are a 0. That job is done by the decoder, and the decoder takes, in this case, two inputs, and it gives you one of four outputs. So what it will do is it will turn three of them off and one of them on, and depending on what inputs you give it, it'll choose this one, this one, this one, or this one as an output. When you put them together, you get a multiplexer, so you have a decoder and a selector. The decoder is here, two inputs, four outputs, one of them's on. This is the selector part. You have the four values coming in that you want to use, and you choose one of them using the decoder. You can also demultiplex, so this is kind of in reverse, where you have a signal coming in, and you choose one of, in this case, four outputs to output that value to. Here's the half adder circuit, and so looking at it, we have an XOR gate and an AND gate. Just looking at the truth table, so part of this truth table has been given. If you want to fill it in, 0 plus 0, that's this case, is 0. 0 plus 1 is 1. 1 plus 0 is 1. And then 1 plus 1, this one, is 0, and then there's a carry coming out here. 0 carry the 1. What that implies is that for the other three cases, the carry was 0 because we didn't need to deal with it. Now if you look at the two gates, this is XOR and this is AND, which is how those two things come in. That's the XOR gate, that's the AND gate. One of the things about this half adder is it's called a half adder because it only does half the job. So if you're looking at what happens here, 1 plus 1 is 0, carry the 1, right? So that goes into the next column to the left. You'll notice though that there's no way for this column here to take another input in terms of a carry coming in. So the carry out for this one becomes the carry in for the next one. So we need to have another part of this circuit that deals with the carry. This part just works on the two AB inputs. So what we're talking about here is the full adder, and you look at how it's built. It's got two half adders. So this is the A and B part. This is A plus B. So A plus B is here, and this is plus C. Whatever A plus B is, you'll add that to C. So you're doing it in a staged way. And we do that very similarly. Like for example, if I'm adding 3 plus 5 plus 7, then what I tend to do is I'll add 3 plus 5 first. That's 8, so that's this part. And then I'll do 8 plus 7, and I'll get 15, and that's this part here. There's a big truth table for it. And basically now we have 3 inputs, so there'll be 8 rows. There's also 2 potential carries, and so they are ORed together to give you the eventual carry out. We also looked at making a subtraction circuit, and so you'll see here that when we're doing subtraction, A minus B is the same as A plus minus B. Because of that, we're actually going to be working on the B part of our expression, so minus B. We start with B, we're going to make it minus B. You'll notice here with our full adder, we're going to reuse it. Now normally a full adder just adds positive values together. So we need to fix it or change it a little bit so that it also deals with this minus B case. So we're going to look at the B input, we're going to add a sign bit, and we're going to put both of those through an XOR gate. And what that should do, based on how this should work, is if the sign bit is a 0, we are doing addition, so B should be unchanged. So A plus B should just work normally. If the sign bit is a 1, then we're doing subtraction, and we need to make this B its negative equivalent. So we need to flip the bits basically. So that's what the XOR gate should achieve. The other thing is when we're using 2's complement, we have two steps. We flip the bits and we add 1. So when the sign bit is a 1, we're doing subtraction. The B bit will be flipped, and you'll see this line coming around here, and it will plug a 1 into the farthest carry in. So a 1 will be added to the eventual value. So let's have a look at how this XOR part works. If you're looking at the XOR gate here, there's two inputs, B and S, or the sign bit. So this is the sign part. So the sign bit can be 0. If it's 0, B can be 0 and 1. So they're the two different cases, and this represents the plus case. So 0 XOR 0. So remember, the 0 or the XOR table looks like this. So 0 XOR 0 is 0, 0 XOR 1 is 1. 0 is the same as 0, 1 is the same as 1. So in this case, when we're doing addition, B is unchanged, and we plug a 0 into the carry-in. So there's no difference to the value. So it works fine for the addition case. Now when we're doing subtraction, the sign bit will be a 1, and in this case, B can be 0 or 1. So let's do the XOR. 1 XOR 0 equals 1, 1 XOR 1 equals 0, and you'll see that the B input has been flipped. It's actually now the opposite of what it was. In addition, the 1 that's part of the sign will go into here, and we'll plug a 1 in here, which is the flip and add 1 component. Here's an arithmetic logic unit. So the only real difference between this and the previous logic unit was that now we have a full adder, so it can do maths. When we're doing multiplication, we can do that fairly easily in terms of multiplying by 2. So if I have a number like this, this is the 1, the 2, the 4, the 8th column, what I can do is I can move this one to one column to the left, that one column to the left, that one column to the left, that one column to the left. Now I have a gap, and so I'm going to put a 0 in there so I don't change the value. And this is the 16s column, so the initial one was 8 plus 4 plus 2 is 14. This one is 16 plus 8, 24. This one is 28. So you can see what's happened. By shifting to the left, I've doubled the number. If I do it again, move it to the left again, I'm going to get 56, and so on. Also works the other way. So if I have this number, 1, 2, 3 here, and I shift it the other way, so this 1 goes here, this 1 goes here, this 1 goes here, that 0 goes here, and that 0 falls off the end. What's happened was this was 28, and now it's 8 plus 4 is 12 plus 2 is 14. So shifting to the right is the same as dividing by 2. Here's the equipment, or the circuit that does that for us. And this particular example is showing this one is shifting to the right. Right, so all the inputs are going 1 to the right, and then we're plugging in a leading 0 or the sign bit if required on the left. We typically tend to want to do more than just multiply by 2, so we typically want to do arbitrary multiplication, like for example 9 times 13. So 9 looks like this, 13 looks like this. And if we work that out, 9 times 30 is 117. So 117, again, I'm just doing the decimal version here. There are no 128s in 117. There is a 64. So 117 minus 64 will be 53. There is a 32 in 53. So what's left? 21. There's a 16 in 21. So what's left is 5. There is no 8. There is a 4. So 4. There's 1 left, so that means there's no 2. And there is a 1. And again, that leads us to 0. So there is a 1 at the end. So this is the answer, 01110101. So again, I did this in decimal just to work out what the answer would look like. But the actual algorithm looks like this. So here's 1001, so 9, times 13. 1101. You'll see here in the columns, this is the column 1, 2, 4, 8. This case, we actually need the powers here. So this is 2 to the 0, this is 2 to the 1, this is 2 to the 2, 2 to the 3. And that's going to be important because those powers will indicate how many times we shift. And the number in this column here, the 1 or the 0 or the 1 here, they will tell us whether we multiply it or whether we keep it in our answer or not. So this is 1001, the thing I'm multiplying, and I'm going to shift it 0 times, and I'm multiplying that by 1 because there's a 1 here. So if you shift anything 0 times, it's going to stay the same. So basically it's 1001. The next one, 1001 shifted once, times, and there's a 0 here, so times 0, well, anything times 0 is 0, so I'm not even going to do the shifts, even though the mechanism might do the shifts. I'm not going to worry about them. 1001 shifted left twice times 1, so basically it's shifted twice, so there's 2 zeros at the front, and then you have 1001. Then the next one is 1001 shifted left 3 times 1. Okay, so there's 3 zeros, 1001. What happens next? You see all these pluses. We add those sections together. So 1001 plus 0 is 1001. 1001 plus the next one is this addition. So it's 101101. And then we need to add the last one. So it's 1, 2, 3. Okay, so we do that addition. 1010, carry the 1, 1, 1, 1. So 1110, looking at our example here, well, there's a leading 0, but it's 1110, So our computation is correct, and again, I've done the check with the decimal version just to see that it was the right value. Then we moved on to arbitrary division, and so we're looking at long division in this example. So we've got 26 divided by 4 is 6, remainder 2. Again, I'm going to put some stuff at the top here just to help me visualize what's going to happen. So we've got 26. 26 is 16 plus 8 is 24, plus 2 is 26, 11010. 6 is that. Sorry, 4. 4 is this, so 26 divided by 4. Answer is going to be 6, and the remainder is going to be 2. So let's do our long division. We'll set it up. This is our number we're dividing by, 4, and this is our number that we're dividing into, 26. So the way it works is we look here, the first one does this 100, does 4 fit into 1? The answer is no. Does 4 fit into 3? The answer is no. Does 4 fit into 6? The answer is yes. So we'll put it under here, and we'll do the subtraction. 6 minus 4 is 2, and it went in once. We grab the next one, 101. Does 4 fit into 5? The answer is yes. How many times? Once. Okay, what's left? 1. We drag the next one down. Okay, 2. There's nothing left over here to work with, so does 4 fit into 2? The answer is no. And so what we've got here is the answer is 6, and the remainder is 2. And that's the end of this section.